and thank you for coming tonight. Our speaker tonight is a distinguished and renowned scientist who has written several books, including his most recent one, The Cycle of Time. He has won numerous awards and prizes, among them the 1988 Wolf Prize for Physics, which he shared with Stephen Hawking for his joint contribution to our understanding of the universe. The title of his talk tonight is Are We Seeing Signals Before the Big Bang? Thank you for coming tonight, Professor, and please could you join me in welcoming him tonight.
Well, thank you very much. Is this working, by the way? Can you hear me at the back? But is it just my voice, or is it just the voice? Let me switch something on. How about that? Any different? No. How about that? Good. Okay. My voices might give out on me, so I have to worry about that. Well, this is another title for my talk, which I think you just saw. So, okay. Now, first of all, I should say this talk is about cosmology, and it's about an idea which I used to refer to as a crazy idea, because I want to get in there first before other people said so. It's actually, let me give you, first of all, a picture of some of the earlier ideas about what the universe was like. These are all after Einstein's general theory of relativity, and when he started to suggest his equations might apply to cosmology. The first solutions were by Russian mathematical physicist called Friedman, and as are most of my other pictures, time is going up the page. So you have to think of space as sections through, and the time is progressing this way. And among Friedman's solutions were one that looked like this in space-time terms. You imagine that the space is closed up. It's really a three-dimensional version of a sphere, surface of a sphere, and I've only drawn it as a circle because I can't draw all the dimensions in there. It started with a big bang, expanded, and then collapsed back to what's called a big crunch, and that bounced and then did it again and again like that. So that was the solution, and people used to call this an oscillating universe, mainly because the radius as a function of time is given by cycloids. So you imagine a hoop, circular hoop with a point, and it's rolling along this line, and the point traces out this cycloid. So you see it keeps on going, and so the idea was perhaps there were cycles in this sense. Now there are various problems with this, one of them being the second law of thermodynamics, because if you have a second law of thermodynamics, the thing called entropy, which is a measure of randomness in some sense, should be increasing all the time. And Tolman, one of the few cosmologists who really worried about this issue, it'll be important in what I want to say, the second law of thermodynamics. And he had a model which was a modification of Friedman's original one, in which these cycles sort of got bigger and bigger. And he did accommodate the second law in a way which made sense. Certainly in those days, when they didn't know about black holes, because black holes are the major contributor to the second law, and that, again, also will be important in what I want to say. Now, various people, in particular Wheeler, worried about whether the constants of nature might get changed each time, and so on. That's not going to feature in what I want to say, but something to think about. Smolin had a version where you had new phases of the universe budding out of black holes, and so on. I have some problem with the geometry not fitting very well. That will be important also, what I want to say. There are other models which are based on ideas from string theory. You'll be happy to hear, maybe, or depends whether you're a string theorist or not, happy if you're not a string theorist, to hear that I won't be mentioning anything about string theory, apart from what I'm saying here, that these two depended on string theory. Steinhardt and Turok have a model which does resemble mine in some respects. Veneziano has a model which certainly my scheme does involve in an important way. Okay, so most of those things I won't have much to say about. But what is the universe like, as far as we know? Well, it's like this. Now this, when I say it's like this, again, it's a space-time picture, time going up the picture. And here, you notice this funny stuff going along the back. These are supposed to be the space sections going up here, time progressing this way, Big Bang there. I'm only putting that at the back because I don't want to prejudice the issue as to whether the universe is closed or open. It might be one or the other. That doesn't actually feature in what I want to say. What is perhaps useful is to see the different spatial geometries that you can have if you have a uniform universe. This is when the curvature is positive. These, I should say, are Escher pictures and models, which illustrate very nicely the different kinds of geometry, of uniform geometry you can have. Of course, these are two-dimensional, and you have to think of a three-dimensional version, but that works fine. It could either be closed up, like the case of the Friedman model, which I was just showing you a minute ago, where you must imagine that these are spatial sections are spheres. Here you have a sphere, here we have the Euclidean case, and here we have the hyperbolic case. People these days seem to be saying that it's flat in this sense on the whole. In a sense, that's the worst possible case because it means we don't really know. It is certainly very close to being that. It might be one of these other models, or it might be something quite different too. But these are, as long as it's reasonably uniform on a large scale, it has to be one of these possibilities. And Escher has illustrated these things with these nice tessellations of angels and devils. I want to concentrate on this one, not because I think the universe is this hyperbolic case with negative curvature, but because this picture illustrates certain things. I'll come back to that later. The main point it illustrates is that infinity here is represented as a finite boundary. So your entire model of the universe is represented as a finite picture with infinity as that boundary, and it's what's called a conformal representation. So that means that angles are correctly represented. Or put another way, if you take a small feature like, say, the eyes of the devils, the shape of that eye will be correctly represented right down to the edge. Okay, it'll be slightly deformed, and the smaller the shape, the less the deformation is, but it just gets smaller as you get to the edge, but the shape is preserved, or angles are preserved. Infinitesimal shapes are preserved. That's what conformal means. We'll come back to that. It's an important concept which will have some relevance. Okay, let's go back to what we think the universe is like now. We have, you might want to know where we are in this picture. Well, we're sort of round about there. I'm not sure. Well, somewhere where the accelerated expansion, which is this part here. So this is the conventional Einstein expansion. The universe expands out here from the Big Bang. The expansion slows down, and then it's supposed to be accelerating in its expansion. This is actually what Einstein's equations will tell you if you incorporate the term that Einstein introduced in 1917, which is he referred to as the cosmological constant. People nowadays give it other names like dark energy and so on, but it's well described by the equations that Einstein introduced. A slight modification of his initial equations. In fact, it's the only thing you can do to his initial equations without ruining them. You can put this extra term in, and this extra term Einstein initially put in for the wrong reason, because he wanted a universe that was uniform, closed up, like the Friedman models with here, but not actually oscillating. So it would be static, in the picture it would look like a cylinder going up here. So it was static. And to make it static, he needed this cosmological term. Now, shortly after that, it was convincingly demonstrated by Hubble and others that the universe is actually expanding. And so that's not a good model. And Einstein was kicking himself for saying, well, if I hadn't put this term in, I might have predicted that the universe is actually expanding. I don't know if he said that, but he did say that he thought his cosmological constant was his greatest mistake. Well, it turns out that even Einstein's mistakes turn out to be true. And it seems that there is this term, and that term very beautifully describes the accelerated expansion that we do happen to see. Okay, now there's another feature of this picture that I want to talk about. You might say, where is it? Inflation. Now, inflation is supposed to have taken place very early in the universe, and it might be that it is there in this picture because it would be tucked into this little black spot at the beginning and you wouldn't know whether it was there or not from the point of view of this picture. So if you want to have a better picture of inflation, you have to get a very, very powerful microscope, well, magnifying glass here. And here I have a picture of what you might see, which is the inflationary phase. Now, the main point I want to make about inflation, apart from the fact that the other reason I haven't got it in this picture, which is that I don't really believe it. If you don't believe it, you have to have some other explanation for what is explained by inflation. Well, some of the things that are explained by inflation aren't really explained by inflation. In fact, the main reasons for introducing it in the first place, though most of those don't actually explain things that, well, I won't really go into that because it's not important for what I want to say. It does explain certain things which you do need an explanation for, and I'll perhaps come to those things briefly later. So you need something like inflation. Take notice that it's very much like the exponential expansion that we do see on a large scale, completely different scale. We do see this exponential expansion taking over in the universe now. As I say, we're up here somewhere where it's just beginning to make its mark. And the claim of inflation is that something very like that was happening in the early stages. But what's different in the model that I'm presenting you with is that, well, in a sense, inflation was there, but it was not there after the Big Bang. It was, in a certain sense, there before the Big Bang. Well, how do you make sense of that? Well, first of all, you make sense of it by adopting two mathematical tricks. And I'm going to try and explain this mathematical trick. Well, actually, the universe would be handy if it was a bit smaller than that for this transparency, so let me make it a little bit smaller. And I'll show you the tricks. The tricks are the following. First of all, you squash down the future infinity to get a finite boundary. Now, that is just the same trick but done to space-time rather than to the space, as Escher was employing. This is actually done first by the mathematician Beltrami. People tend to, in mathematics, they tend to call it the Poincaré representation. It was actually due to Beltrami a good deal before Poincaré, but never mind. Poincaré rediscovered it, so that's reasonable fairness about that. Anyway, so you can sort of squash infinity down in that same way as in that picture, but now to space-time. I'm squashing infinity down to this boundary. It's just a trick. What's the other trick? The other trick is to stretch out the Big Bang also to get a finite boundary. That's the opposite trick to the one that Escher was showing you in his picture. Now, there's a little bit of a difference in status between these things, in a logical status. The difference is explained here. One is the future trick works very, very generally. It's really no restriction on the universe at all. If you've got this positive cosmological constant, this exponential expansion, and the universe thins out, and there's nothing much left except photons and things which don't have any mass and so on, then this will always work, this trick. There's a theorem due to Helmut Friedrich, who has demonstrated this pretty convincingly. Now, that requires positive cosmological constant, which is what we seem to have. However, the other trick, the stretching out of the Big Bang, is a huge restriction on the nature of the Big Bang. So here we see an extremely strong restriction, which corresponds to suppressing gravitational degrees of freedom. And the generality of that, or lack of it, is exploited by my colleague Paul Todd, and I'll come back to that and say why it's important. Now, these two tricks, I should say, are nice things you like to do. Whether they have any physical content is another question. They're certainly nice ways of looking at the universe as a whole. You can sort of draw it on one piece of paper if you like, which is rather nice. But I want to use it in a more dramatic way. I say that this thing that I'm doing here, I have to get the right one out. Here we go. The two tricks which I'm employing here are, in a certain sense, real. And not only that, but they are part of a progression of universe. Well, I'm calling these eons. So each one of these is an eon, and each eon starts with its Big Bang and ends with this infinite exponential expansion. But the idea is that when you squash down infinity, it looks very much like a stretched out Big Bang. And that's rather remarkable. But I'm asserting more than that, that it is actually, the stretched out Big Bang is a squashed down infinity. If this is us here, and we're sitting here somewhere, then there was an eon prior to ours whose remote future became our Big Bang. our remote future will become the Big Bang of the next eon, and so on. And this may be extended indefinitely in both directions. Now, I want to try and justify, first of all, Todd's trick here. Why is it that we can get away with making that infinite expansion? Well, the point is really to do with the second law of thermodynamics, as I mentioned briefly before, but I want to say more about it. In fact, I want to talk about two things about the second law of thermodynamics, two things which have to do, I should say, with the microwave background. You see, we now talk about the Big Bang very glibly, and they say there's lots of evidence that it was there. But what is the strongest piece of evidence that the Big Bang was there? Well, the strongest piece of evidence, basically, it was the piece of evidence which was main one in disproving the older steady state theory, which I grew up with rather in my young student days. The point is that there is this radiation coming out in space from all directions, which is basically photons, and, well, they are photons. It's electromagnetic radiation coming from all directions, of indicating a temperature of something like 2.7 degrees above absolute zero. So it's very cold. It was seen, I say, it's won the Nobel Prize twice, on two separate occasions. First for the original discovery by Penzias and Wilson, who discovered it by mistake, in a sense. Although it was there, it was predicted that it should be there by Dickey and Gamow people. The idea was that in the flash of the Big Bang would produce this radiation, and as the universe expanded, so here we have this flash of the Big Bang, as the universe expanded, it would have cooled the very, very hot radiation that it was originally to this 2.7 degrees above absolute zero. And the two features about this, first of all, the thermal spectrum. For some reason, I don't seem to have my slide that I would have shown you here. I didn't find that one. I didn't realize it was missing. But there is if you look at the temperature, the intensity of the radiation for various different frequencies, then you find a very nice curve, which is the Planck radiation curve. And the Planck radiation curve is telling you that what you're looking at is thermal equilibrium. Now, there's a bit of a paradox here. I was talking about the second law of thermodynamics. The second law tells you that randomness, or entropy, if you like, is increasing with time. Now, another way of saying that, you see, if entropy is increasing with time, then another way of saying it is if you go back in time, entropy is decreasing. So that means that the entropy must be very, very small at the Big Bang. And it has to be, just for very, very basic reasons, the fact that we have a second law of thermodynamics, and that we believe that that second law was still holding way, way back into the Big Bang. Now, if that's the case, then the initial Big Bang must have been very, very special, very low entropy, at least in some particular respect. And what we see, the evidence for that Big Bang, we see this beautiful Planck curve, the most perfect Planck curve ever seen in any observation. What does that tell us? It tells us that what we're looking at was thermal equilibrium. What's thermal equilibrium? It's maximum entropy. Now, that might seem to be a puzzle, but for some reason, cosmologists hardly ever worried about it. Well, Tolman, I did mention, did. He's one of the few who really did worry about this question. But for some reason, when you see what the problems of cosmology are, and there could be a list of them, the second law is never mentioned. I never understand that, because it is a huge mystery. But the mystery isn't quite the way I'm putting it. You see, you might say, how could it be that this maximum entropy state, which we seem to see in the Big Bang, that's what the Planck spectrum is telling you, it's a maximum entropy state, maximum disorder. How can that be the very small entropy that started the second law off? It's not a contradiction, it's just a puzzle. And I want to tell you what that puzzle is. Why is it not a contradiction? Well, I think some people used to argue without thinking that it's got something to do with the universe expanding, and that maybe there were wasn't room for much entropy in this world. That's just a wrong answer. And Tolman certainly appreciated that. But I'll give you another better reason for why it's the, well, not better, but another reason why it's the wrong answer. Now, okay, if that's not the right answer, what is the right answer? Well, you have to address the question of what you're looking at. You're looking at photons. And those photons are coming from their interaction with matter. So you've got matter and radiation, apart from the expansion, which is basically adiabatic. That's what Tolman pointed out. So the fact that the expansion is there is neither here nor there. It really is, modulo the expansion, if you like, a maximum entropy state. But what's the other feature of the microwave background? The fact that it's a thermal spectrum is one thing, but the other thing is that it's almost exactly uniform over the whole sky. Now, almost exactly uniform, well, it's not quite uniform, but the major way in which it's not uniform is due to the Earth's motion. So the Earth is moving through it, and when you correct for that, you get something which is extremely uniform. It's uniform. The temperature is the same in different parts of the sky to a few parts perhaps in 100,000. So a few parts in 10 to the fifth. Very, very uniform. Now, I'm going to be saying something about the little ways in which it's not uniform later on, but that's completely swamped by the fact that it is uniform. Now, what's that telling us? Well, again, you might say it's telling us you're looking at high entropy. Well, you see, when we talk about the second law of thermodynamics, the sort of thing you might talk about is a gas in a box. And you might imagine that if you had a little compartment here and all the gas was in that compartment with some walls, you remove the walls, and then the gas will spread out through the box. So uniformity certainly is an aspect of large entropy. So as the uniformity increases, the entropy also increases. So that's consistent with high entropy. You're back where you started. But suppose these were not molecules in a gas, but suppose you had a galactic scale box, if you like, and you're looking at stars. And those stars are gravitating. Now, if they were uniform originally, there would be a strong tendency for them to clump and become less uniform, simply because gravity is a universally attractive force. And now, entropy is increasing with the increasing clumpiness. Now, what do we see? We see uniformity. That is consistent with this picture and with this picture. So you're seeing a combination of high entropy in everything except gravity. Gravity, which was the thing that was not thermalized, it somehow remained aloof from everything that was going on. It was stuck at a very low value in the initial state. Now, the thing is, people didn't kind of think about that much because the models, such as Friedman's, for example, they assumed uniformity in order to solve the equations. If you're going to solve Einstein's equations, they're quite difficult. The good thing to assume is that it's a very uniform universe. Turns out the universe is very uniform. But see, people have forgotten how big an assumption that is. And I'll come back to that issue too. It's a huge assumption. And that is the thing. Here's the mystery. The mystery is, why was it that everything was high entropy, in other words, all thermalized, except for gravity? It's not a contradiction, it's a mystery. And it seems to me that is one of the biggest mysteries of cosmology. Nobody ever mentioned, well, I do, but nobody ever seems to mention it. Now, this clumping is a feature which is what we all depend upon, and just to make that clear, why are we all here? Well, a good reason why we're all here has to do with the fact that the sun is here, and the sun is a source of low entropy, and you can think of that as the fact that, well, you see, people think, what's the sun for? What do we get from it? Well, we get energy from the sun. That's not really correct, because the Earth as a whole throws away just about the same amount of energy as it gets from the sun. If it didn't, the Earth would just get hotter and hotter. Well, it's getting a bit hotter through global warming, but that's relatively small on the scale I'm talking about here. If it wasn't the fact that the energy from the sun didn't go out again into empty space, we would just be all frazzled away. So we have to lose that energy. But what the key point is that entropy, you see, the sun is hot, the background sky is cold. That means the photons from the sun are high energy. The photons which go back, these are sort of yellow photons, and the photons going back are infrared. These are much less, individually less energetic, so therefore there are many, many more photons to carry the same amount of energy coming in. This means more organization. Or if you go to the definition of entropy, fewer degrees of freedom here, many, many more degrees of freedom here, and so the energy is thrown away in a high entropy form. So that what we get from the sun is a source of low entropy. That's the key. And, well, why is the sun there at all? Well, why is it hot? It's hot for all sorts of reasons, because of thermonuclear reactions and all sorts of things. But the key point is it's there at all, and it's there at all because of gravitational clumping. It's the previously uniform gas was clumped into the sun, and that heated up, just the mere fact that it was clumping. In fact, if there weren't any thermonuclear reactions, the sun would have got much hotter much quicker, and then it would have cooled off. It wouldn't have been much use to us, but it would still have got very hot. So the point is, the thermonuclear reactions actually slow it down so the sun can stay there for a long time and keep us warm, but not, the main point is that they keep the entropy down. Plants make use of that by photosynthesis, and then ultimately we eat plants, or animals that eat plants, and so on. And that's how it all works. Okay, let's just indicate that this gravitational clumping is an important feature. Now I want to go back and talk about what's the sort of maximum entropy state. Well, it's a black hole. So the black hole is where the entropy finally ends up. And in the present universe as we know it, by far the major contribution to the entropy of the universe is in black holes, is in the supermassive black holes such as we have in our galactic center, and other galaxies also have black holes in their center, which have a huge, absolutely enormous amount of entropy contained in them. Now, I want, therefore, to say something about black holes. So let me give you a picture of a black hole. And my picture of a black hole, like my other pictures, most of them will be a space-time picture. Here we have time going up the picture. And here we have some collapsing material to make a black hole. And this is the horizon of the black hole. Now, the main thing about this picture, well, two things which are important. One is, if you like, the horizon, or that is a feature of the light cones. So the important thing is to know what the cones are. The light cones, well, you can think of at each point in space-time there is one of these double cones drawn on it. Of course, you've got to have the right number of dimensions. Here I've thrown one away to draw the cone. This is a spatial picture. If you imagine the flash of light taking place here, then the history of that will be described by this future cone. Spatially, it will be a point, and then this section corresponds to there, and this section corresponds to the sphere beginning out there, expanding with the speed of light. There's also a past cone, which represent what light would do. You have to imagine every point there's one of these cones. There isn't necessarily light there. It's just telling you what light would do if it were there. And to understand special relativity, you just imagine these cones uniformly distributed throughout the four-dimensional space-time. General relativity, they're not uniform. They're kind of all higgledy-piggledy. In each case, you have, well, the cone is the future part and the past part. A photon has a world line, that's the history of that photon thought of as a particle, which will be tangential to the cones all the way along. And then there are massive particles which are always within the cones, telling us that the massive particles have to have a world line which represents a speed which is less than the speed of light. If these cones are tipped over in various ways, the particles have to be constrained to have their world lines within the cones, however they are tipped. And again, the photons along the cones, the massive particles within the cones. So we need that. And now that just shows us a bit more about what's going on here. And the horizon has this rather uncomfortable feature that it well, you see the light cones are all tilted over this way, pointing inwards. And if you were unfortunate enough or foolish enough to happen to be in the neighborhood of this horizon, you would then find yourself trapped inside. And you can't get out because any world line that draws itself outwards would have to violate the causality condition, because it has to be constrained to be within the cone. The other, even more unpleasant feature is that you will shortly encounter the singularity in the middle, where the space-time curvature becomes infinite, densities become infinite, all hell breaks loose, the equations find themselves giving up somewhere down in the middle there. So because curvatures become infinite, densities become infinite, and so you're stuck. Okay, that's the black hole with its singularities in the middle. Or at least, this is just a picture mainly got from the spherically symmetrical case. In general, there will be irregularities. Those irregularities, we know from theorems that they will still result in singularities, even though the picture won't be exactly like that. Okay, our picture of the universe now has to be modified. Here we have the singularity of the Big Bang, where the space-time curvatures also were infinite. And we have the singularities now in the black holes, which will be in various places. Now, the point here about the second law is that the singularities in black holes are of a character where you could say the entropy is enormous. And that's true in black holes from the famous Bekenstein-Hawking formula for the entropy in a black hole is an absolutely enormous figure. And that is, in a sense, telling us that when you get to the singularity, you will have a very, very gravitationally random state. So it's very, very high entropy, quite unlike what you see at the Big Bang. In fact, it's the singularity structures which drive the whole thing. It's the Big Bang happened to be a singularity of a very special kind, which is not shared by the singularities in black holes. Now, you see, I can kind of make the reason why, if you like, inflation and any of these other arguments don't give an explanation of why the black hole was so special. It's really just the second law. I want to imagine, just theoretically, that the universe was collapsing. Let's suppose it was, but with a second law, which is still going in the same direction, upwards. Now, black holes will then form, and these black holes will meet each other, swallow each other up, congeal, and form one incredible mess at the end of congealing singularities. So that will be the picture, something like this, with entropy going up and up and up and up to some ridiculously enormous value when all these black holes congeal with each other. Now, if you put inflation in, which is supposed to be due to some special field called the inflaton field, which is supposed to smooth the universe out, well, you can see it can't do that, because what would happen if you reverse this? Well, you just get this mess. And that means that would have been a much more likely initial state for the universe, where it started out very, very general, and inflaton fields don't do anything for you. So that's the whole big problem, is why was the universe initially like this and not like that, where the likelihood of it being like this is absolutely enormous. In fact, let me give you some idea of how absolutely enormous it would have been. Okay. The Big Bang must have been subject to an absolutely huge constraint due to the suppression of gravitational degrees of freedom. And you can work out from the Bekenstein-Hawking formula for the entropy in a black hole how special that state was. Let me not go into the details of that. It's not a difficult calculation or anything. It's just, it's the answer. The answer is that the improbability of finding the universe anything like the way we did find it is about 1 part in 10 to the power 124. You may see this figure as 123 somewhere, not that it makes much difference to the, it makes absolutely stupendous difference to the actual number, but hardly any difference to the argument whatsoever. This is because if you include dark matter, then the number goes up to 124. You may see 123 quoted in some places. That's without the dark matter. That's the only difference. Okay. The reason for the double exponent has to do with the definition of entropy, which involves a logarithm. I won't go into that here. But this is giving you how unlikely, if it was just chosen randomly, how unlikely anything like the universe that we actually encountered had at the nature of the Big Bang, that sort of unlikeliness. Now, let's not worry for the moment about how that could have come about. Let's just address the question of what was it like. How would you describe geometrically what that universe was like, specialized in that way? Well, there was a thing I used to phrase it in this way, the Weyl curvature hypothesis. The trouble with that is you need to know what the Weyl curvature is, and I haven't got time to explain that to you. So let's not do it that way. Fortunately, there's a better way of doing it. It's an awkward condition to state, just in terms of curvatures. But Paul Todd, my colleague in Oxford, in 2003, came up with another way of saying it, a very mathematical, elegant mathematical proposal. Well, I've cut the piece of the transparency off here, so I'm going to show that to you only in a little while. Let me worry for the moment, not about what the Big Bang was like, but the other end. So we'll think about not just why the universe was like this and not like this, but what about the remote future? Well, the remote future, first of all, things will fall into black holes. Black holes get bigger, galaxies collide with each other, the black holes get bigger still, and a lot of matter will, well, this exponential expansion will thin the universe down. You'll have black holes and the matter thinning it down in the remote future. What happens to the black holes? Well, according to Stephen Hawking, and I certainly agree with him, when the universe, you see, black holes are not entirely cold. They're pretty cold. In fact, well, I think Stephen wrote an article calling black holes are hot. How hot are they? Well, it depends how big they are. The bigger they are, the colder they are. The smallest black holes, therefore, will be the hottest ones. What are the smallest ones we have any reason to believe in? Those are a few solar masses, a few times the mass of the sun. What is the Hawking temperature of those black holes? Well, you have to think, to get the right sort of ballpark figure, you have to think of the coldest temperature ever produced artificially on the Earth. And that's the sort of scale. Very, very, very cold. But these are the hot ones. The really cold ones are the supermassive black holes like the 1,000,000 to 4 million solar mass black hole in our galactic center, or the far bigger ones that people are detecting in other galaxies. And the thing is that when the universe expands by this exponential expansion, it will get colder and colder, and the microwave background will become colder and colder until it gets colder than any black hole that we have any reason to come about. The really huge supermassive black holes. And you have to think of a time scale of something like 10 to the 100 years, or a googol years is sometimes called. 1 followed by 100 zeros. And in that kind of time scale, or maybe longer if there are even really bigger ones, the black holes will evaporate away because they will be the hottest things around, and when they're the hottest things around, there will be thermal radiation coming from the black hole, very, very cold, long wavelength, photons mainly, long wavelength photons will be carrying away the mass very, very slowly to something like a googol years, and as they carry away energy, they must therefore carry away mass, and therefore the black hole will get smaller and smaller and smaller until it goes off with a pop. Well, I've called it a pop here because although it's quite a sizable explosion, it will not be anything of significance on the astrophysical scale. So even if, well, the final pop is only about an artillery shell, but I guess you have a fairly big explosion before that when you lose something like a nuclear explosion. But that's chicken feed with regard to things on a cosmological scale, so I'm calling it a pop. Okay, so what's our picture look like now? Here is our universe, as before, and now I'm putting black holes in, and they're going off pop. Now this, I should say, is grossly not to scale. I mean, it's way up there somewhere. The other point I want to stress here is what I have rather written here. This is when they've all gone, this is what I call the very boring era. Now, you see, it's pretty boring already when there's nothing much going on except black holes. And I can't think of anything that's more boring than sitting around waiting for, maybe a googol years, waiting for that black hole to go off pop. Seems to me rather boring, but that's nothing compared with how boring it's going to be after that. Now, I use an emotional argument at this point. Okay, I admit it's an emotional argument. I think that somehow that's not a very satisfying picture. You know, the universe is all very exciting now, wherever we are up here. And just to imagine that that is the fate of the whole thing seems to me to be pretty miserable. But then I began to think, Well, who's going to be around to be bored by this? Not us. The main things getting around, by far the main things will be photons. And it is incredibly hard to bore a photon. There are two reasons why. One is probably doesn't have any experiences, but the other is the basic thing about relativity. See, here we have, so I've drawn the light cones. I've talked about light cones up to this point, but what I haven't talked about is the rest of the structure, which gives you the metric which Einstein needs to describe his space-time geometry. The metric component, the metric is the thing that's sometimes written GAB or G mu nu or G alpha beta or something like that. And it has 10 independent components per point. 10 numbers characterize it at each point. 9 of those numbers, or at least the ratios of these 10 numbers, simply just telling you where the cone is, exactly how it sits and how fat it looks in your representation and so on. It's just telling you what light does. So 9 of the components are telling you the light cones. The 10th is the scale. Now, you see, if you want the metric, suppose you want to describe how big things are in relativity. Well, you might say, well, you want to measure distances, and distances need rulers, and then you might measure ruler distances by taking, well, you say meters. And how big is a meter? Well, then you go to the meter rule in Paris. The trouble is that's not much use anymore because it's not very accurate by the kind of standards that we have nowadays. A much better way is to use a clock and the speed of light. Clocks are the things which determine the scale. Now clocks, I've put them in here in this picture. I've got 2 identical clocks going through this point, and this represents the first tick, that's the second tick, and the third tick. So you need to add to your light cone these sort of surfaces here, and the crowding of them is the 10th component. Now you see, we have very good clocks in physics. It's one of these amazing things that the 2 most important simple equations of the 20th century physics, Einstein's E equals mc squared, and Max Planck's E equals h nu, nu being the frequency, E being the energy, m the mass, m, h, and c being constants. Einstein tells you that energy and mass are interchangeable. Planck tells you that energy and frequency are interchangeable. Put them together, tells you that mass and frequency are interchangeable. So if you have a particle whose mass or rest mass is m, that determines quite uniquely through these formulae a frequency, m times c squared over h. And so it's an oscillator. Very, very well defined in terms of its mass. And that is basically how, ultimately, it's the mass which tells you how our wonderful clocks, our atomic and nuclear clocks, depend ultimately on this very fundamental concept of time, which comes from those very fundamental equations which come from the mass. So if you have mass, then you have a time scale. But if you don't have mass, as is represented by this photon, there is no measurement of time. The photon doesn't know the progression of time at all. So as far as the photon is concerned, well, one way of putting it is infinity is no big deal. You see, the photon doesn't even know the passage of time, but it goes right up to eternity, and as far as it's concerned, nothing much has happened. So if we imagine photons, they're not bored at all. If they are allowed to have feelings, they wouldn't be bored. Another way of saying all this is, here I go back to the picture I had before, and what I want to do to it is make it a little bit more complete. Because if we take the representation here, it's only the light cone structure. That's actually the conformal structure. Remember the angels and devils in the Escher picture? This is the space-time version of it, is just to know the light cones. That's the conformal geometry. It doesn't know the scale. If you want to know the scale, you put your clocks in, and here we have them at the top here. There's a clock, and this gives you these surfaces, hyperbolic surfaces here, and the crowding of them is giving you the full metric now. Now, a lot of physics, you might even say most of physics, doesn't need the scaling. If you don't have rest mass, you just need the conformal structure. This most dramatically applies to Maxwell's equations for the electromagnetic field. They are completely invariant under change of scale. You can change the scale arbitrarily in different places by different amounts, and the Maxwell equations come out completely unscathed. So they don't know, they don't even care about the scale. It's also true of the Yang-Mills equations, which have to do with strong and weak interactions. The only sort of difference there is that mass comes in an important way. It's the mass which knows the scale, and when mass is there, you have to know the scale. When mass is not there, this is the kind of geometry you want. If mass is there, you need the whole geometry. Well, mass in another way also features as the source of gravity, and as the source of gravity, it's important in general relativity. So you need to know the mass, you need to know the scale for general relativity, but then gravity, it's again mass because it's now the source of gravity which is involved. Okay, now if you just have the conformal structure, I was saying in the very remote future, it's mainly photons that are around, and so it's the conformal geometry which will be important. And if it's the conformal geometry that's important, then you can go back to this picture and say, okay, infinity can be squashed down, and what the physics doesn't really know. Unless it's physics with mass in it, if it's physics without any mass in it, it doesn't really care that this is a boundary, it's just like anywhere else. So that's the philosophy, and so one can think of the very remote future as being, and this is a trick that we've used for a long time, is to squash infinity down. If you want to talk about radiation in general relativity and so on, it's been a useful trick to squash infinity down and talk about the Maxwell field, what it's doing on this boundary. And that's sort of asymptotic properties of the Maxwell field. And this trick will work here. Okay, it's just a trick. You treat the extremely remote future, squash it down, and it's handy. Okay. Now I'm trying to say with only massless things, conformal geometry is important. Well, there is a little bit of an issue here. Because although most of the particles lying around will be photons, there will be massive particles too. Some of them might decay, maybe protons decay, but you can't very well get rid of the electrons because there's nowhere for them to go. Electrons and positrons you'll be stuck with. Maybe they'll be pretty scarce, but they're still there. So that will spoil this picture. So I'm going to propose, and this is an unconventional proposal, that mass itself will gradually fade out in the very, very remote future. It's a sort of reverse of a Higgs mechanism that when the temperature gets very, very cold, then the mass will fade away. As I said, it's not conventional, but there's no evidence against it. And then the conformal geometry would be what's important. And so you have a future boundary. And then you might say, well, what's on the other side of that boundary? Or the question is, what was there? Go back to what Todd's proposal was. What is Todd's proposal? Well, it's this, that the space-time can be represented conformally, so if you forget about the scaling, so that the Big Bang was a smooth surface. And in fact, that does kill off all the gravitational degrees of freedom. That's a technical point which I can't go into, but he was regarding this as basically a mathematical trick, a way of formulating the condition on the Big Bang that corresponds to the low entropy in gravitational degrees of freedom, can be high entropy in everything else. There's lots of things running around here, but it was just a mathematical trick. What I'm saying is that these tricks are real. That there was something before the Big Bang. It couldn't have been a collapsing universe, which might be the most obvious thing to think of, because then you're in trouble with the second law, because the great mess which I showed you for the collapsing models will give you something which doesn't stretch out to become smooth. That's basically what Todd is saying, that if you want to get rid of the gravitational degrees of freedom, you have this smooth boundary. And so anything where the gravitational degrees of freedom are piling up and producing this great congealing of black hole singularities isn't going to be any use for back here. It doesn't explain this state. I mean, you could say, well, it heads for this in some sense, or maybe the second law went in the opposite direction, back this way. But it doesn't explain why there was this very special state. However, if it was the continuation of the remote future of something before it, then you look at the equations and you see, yes, the gravitational field is cooled off. And it just comes from the way things transform under these conformal maps, and I won't really go into that here. So that's the picture, and then globally, this picture is the one I showed you here, that our Big Bang was the continuation of the remote future of something before, and in a way, this enables you to get away with not having inflation. Well, why does it do that? Well, you see, you have the exponential expansion of the previous phase, and that looks rather like inflation. So inflation does explain certain things. There's a thing called the scale invariance of the fluctuations in the microwave background is the sort of thing that you need inflation for, or else something else which does it also. And I would say, although there's a lot to be checked in this, that the exponential expansion of the previous eon does, in that respect, what inflation would do in the more conventional picture. So that's the idea. One question you might well ask is the Tolman question. What's happened to the second law of thermodynamics? If entropy is increasing and increasing and increasing, how can you have a cyclic model like this? Well, here is where you have to bear in mind where most of the entropy was, or is, I should say, already in the universe as we know it. It's in black holes. What happens to the black holes? They evaporate away. Well, does that violate the second law of thermodynamics? No, it doesn't. But you have to be careful. And what I'm saying is you have to be very careful. And it goes back to something Stephen Hawking said in, I don't know if I've got the date down here, but it was a long time when he first put forward these ideas. And he said information, or phase space volume is really what it is, gets lost in the singularities in black holes. And then he changed his mind. And much later he said, no, somehow, I feel he got browbeaten by other people who wanted the entropy, somehow information not to be lost. And so he changed his mind later. I think he was right originally. The original thing, and you look at some of these diagrams and you can see, yes, information does get lost. It gets swallowed into the singularity, and there's no way around it as far as I can see. Now, what does this mean? This means that when you define your entropy, you have to worry, do you take into account those degrees of freedom which are swallowed by the black hole, or don't you? When the black hole is gone, there's hardly any point in taking them into consideration, and so you change your mind about what your definition of entropy is. It's sort of a renormalization of the definition. You subtract a huge number from the entropy, which corresponds to the loss of degrees of freedom in that black hole. And if you do that, you get a consistent picture that the second law is never violated. It's sort of transcended in a sense. That the second law drives, in fact, most of what you say about black holes. It's not violated. It more or less, you don't even need to know much of the physics. The second law is almost all you need to know. It tells you that what the black hole does, it has a huge entropy. It disappears because it has a temperature. The temperature goes up as the black hole gets smaller. And what happens to it? Well, if it disappears, it will carry away from our universe those degrees of freedom which it swallowed. And then you say, I'm not interested in those degrees of freedom anymore. I'm going to define my entropy without taking them into consideration. And that brings the definition of the entropy down. So that by the time all the black holes have gone, it's silly to use the old definition because those black holes have swallowed all those degrees of freedom. The definition that you now use is back down to the value you need to have the low value that we get for the next eon. All these things need more detailed examination, but it seems to me that they are consistent as far as I can tell. What about observational consequences? Well, I tried to think, what could possibly be a signal which gets from before us? This is the crossover surface between the previous eon and us. It's really a three-dimensional surface, but I've drawn it as a plane here. This is up here, us up here. We look back to the microwave background, which is just a little bit after the crossover surface here, and what was going on before, that we might possibly see. Well, what's the most violent thing I could think of? Apart from the Big Bang itself, if you like, the most violent thing in the previous eon would have been collisions between supermassive black holes. I mentioned before, we have a black hole in the center of our galaxy, which is about 4 million times the mass of the Sun. We are on a collision course with Andromeda, and an even bigger galaxy than us, with a black hole in its center, which is about 20 times as big as ours. When they collide, it won't be anywhere soon. Well, I tend to say, thank goodness it won't be anywhere soon. Somebody said, well, that's a pity. It would have been rather dramatic to see this collision. I kind of think, yeah, it would be rather dramatic. You can see simulations on the web, incidentally, what it might have looked like. Might look like, I should say, in the future. When we hit Andromeda, well, you see there's a lot of empty space in Andromeda, so we're not likely to hit anything, apart from maybe some dust or something. But the black holes are quite likely to capture each other. They'll spiral around and finally swallow each other up with one stupendous explosion. That explosion will be mainly in the form of gravitational waves. That is the gravitational version of light, ripples in space-time. And I've drawn in this picture, these are the black holes coming spiraling into each other, poof, bang, well, don't know how to call it, walloping bang. And there is a few percent of the rest mass of the black holes will be carried away, which is pretty huge. And that will be carried away on the sort of scales we're talking about here almost instantaneously. And this explosion will come up and hit this crossover surface. Well, then you've got to look at the equations and see what it does. It transfers itself from a gravitational effect into a kick given to the initial form of dark matter. There has to be some creation of some scalar substance in order for the equations to make sense. I'm calling that the initial form of dark matter. We don't really know if it behaves like dark matter, but since nobody else knows what it is, I can more or less suggest that it is something which automatically comes about to accompany the gravitational field. It has to be there, otherwise the equations are inconsistent. It will acquire a mass due to some form of Higgs process, I presume, and then it becomes like the dark matter we see. Well, by the time you see it in the microwave background, this impulse will be rather deadened, but in the form of giving that initial dark matter a kick, a velocity. And what you would see, something like looking at ripples on a pond. So this is the microwave sky, and I claim that each one of these black hole encounters will be like a ripple in the pond where, say, a drop of rain had hit, and it gives you a circular ripple. And you imagine the rain stops after a while. That's when all the black holes have gone here. And then you just look like a pond, which is ripply all over the place. And that's the microwave background, so I say. But then you ought to be able to see, if you do some clever enough statistical analysis, that these ripples were still, the circular patterns are still hiding there and can be extracted if you look at them in the right way and do the right analysis. Well, one point, I had tried to get people to do this, and it was very hard to get people to look at it. But my Armenian colleague, Vahe Gorzajan, did look for these things. He looked in a slightly different way from what I was expecting. He looked for regions where the variation of the temperature is as anomalously low around circles. But in order to get a significant effect, you have to look for concentric sets. Now, you see, why would you expect to see concentric sets? Well, because if you have one of these supermassive black holes, it's liable to swallow others, another one and another one and another one, and then each time you might get the supermassive black hole encounters, which will produce these explosions which will look like concentric rings. So the idea is, do you see concentric rings? Well, he was looking for low variance, or do you see a temperature which is either slightly warmer than the average? That would be from a distant source when the signal is coming towards us, and the initial dark matter is a velocity in our direction, or those are the warm ones, which are from very distant sources, or the near sources, the signal will be cooler because it's giving the microwave background material a kick in the opposite direction. Now, we finally, after lots of arguments with referees and so on, hit on this way of looking at things. This is a way of testing whether the thing is real or not, that you look at the sky and see how many of these circles you see which have this particular criterion of low variance. And then you look again at a slightly twisted sky. So I imagine you twist the sky, the twist goes more and more as you get down to the bottom. And that twist makes the circles into slightly elliptical shapes. And then you apply the same analysis. So basically, you're now looking for elliptical shapes in the real sky. And you can make the twist bigger and bigger and bigger. If this twist value S is 2 or 5, or something like that, you're looking for ellipses which are almost circles. The ratio of the major to minor axis differs from 1 by 1 or 2%. Right down to when S is 80, which is the biggest we looked at, where you're really looking at ellipses which look like ellipses, with the major to minor axis ratio is about 2. So that's the kind of thing we're looking at, and I hope I can get the... Before I go to that, let me, since I may not easily go backwards and forwards, this was, after we did this analysis, some people in Poland, a chap called Meisner, who, with some other people, did a different kind of analysis, much more like what I'd originally suggested. And he looks for signals which have a sort of front. You see, it has a sharp edge on the front, and then it tails off one way or the other. And so you see the sharp edge on the front. See, this is the gravitational wave coming up here. Here's crossover. It's become a kick in the original material. When it acquires a mass, it starts to, the viscosity comes in and it acquires a tail. And so you see a sharp front here and tailing off. So you have a spike. That was the idea, and this is the picture here which is trying to indicate that. And so you will see certain profiles that you might be able to see in the microwave background. I'll come to that in these pictures here. What do people actually see? Well, originally, now I want to get this working. Do I press something to make it working? Now let's see. Do I need the screen, or is it? You better help me, because I'm not quite sure.
Do you want to see this first?
Yes, just that one. Yeah, that would be. Yes, I think so. Is that the first one? It probably is. Yes, yes, that's right. That's right. Yes, yes, that's it. Fine. Okay. Oh, it's on the screen. Yes, that's fine. Okay, good.
Should be.
Okay, well, this is what Vahe Gerzajan found in the actual sky. You have to bear in mind this is the entire sky. The bit in the middle is the galactic plane. He just said we don't count these signals which come to us from within this region, but we count them if they're outside the region. You do count circles if the major part of them is outside the region, as long as the center is outside the region. The galactic center is there, and this is the entire sky sort of unwrapped. It's a standard sort of projection. Now, initially, he was looking for concentric sets of circles which are of low variation. So he's not looking for warm or cool particularly. He's looking for circles where the variation in temperature as you go around is smaller than on the average, and significantly smaller. That's the idea. And that would be the kind of thing you would expect in this picture, but not looking for the average temperature. When they're redder, it tends to be ones which are warmer, and therefore in my picture would be sources which are further away. If they're blue, that means they're cooler. It's the wrong way around. Red shifted, you see, is the blue ones, and the blue shifted ones are the red ones. But that's the way, I'm afraid, that color scheme works. Okay, we see 352, I think it is, circles in the sky, in the true sky. Now, to see whether this is a real effect, first of all, you can look at a simulation. This isn't the one I was expecting to see. That's a general simulation. You see far fewer in a simulation. But that was not the way we were doing it. So let me see. I guess I have to press something to go back, do I? Yes, you better help me, because I'm no expert at these things, I'm afraid, as you can tell. How do I go to one of the other? I'm not sure this is the first picture, is it? So, can I do the first one?
Sure.
Yeah, that's it. One? Yeah, it is the same as that picture, actually, but the top one, that's it. It is the same as the right-hand one at the top. Okay, that's fine. I can move it, I think. Okay. The left-hand one just shows where the centers are. The first thing which is rather prominent about that is that it's very non-uniform. And the conventional explanations, you see, the conventional explanation for the fluctuations of temperature in the microwave background are that it's some kind of quantum effect expanded out by the inflation. But if it's a quantum effect, sort of random, why do you get this crowding in certain regions? I was not expecting to see crowding at all, but seeing it, I can give you an explanation. It's just that in the previous eon, there were regions where there were huge concentrations of extremely large galaxies, and with very, very big black holes in their centers, and those were the ones that caused the signals that we actually see here. And this represents a very crowded region here. There's another crowded region there, and then some other ones. This would be a distant one on my scheme because it means, because you see red ones. So it's they are blue shifted, the signals are coming towards us. This is a closer region here, which is red shifted, in other words, blue in the picture. That's the interpretation I would give. Okay, now we start to twist. And you see, rather than the 352, the number at the top there you see is the number of centers we see of the at least 3 circles with the same centers, 3 low-variance circles with the same centers, 352 of them. You twist, and remember that this is a twist where you're only looking at 1 or 2% away from a circle. It drops by a factor of 3. As the twist goes up, the numbers drop, and they drop quite consistently right the way down to when you get to the bottom. It's the sort of numbers that you would see from a random sky. So these numbers probably mean nothing. You see, the ones that you're seeing at the top we claim are real. On the whole, most of them are real, but the ones at the bottom are not. Okay, now to move myself to the next slide, if I press something, I'll press the wrong thing. So is it this arrow here? No, it's not.
So do you want the?
Oh, it's on the mouse. Okay.
That one.
Yeah, that one. Yes, that one. That's fine. Yeah. Okay, good. That's it. Now this is for 4 concentric circles, centers with at least 4 low variance rings, and we still see 56. Start to twist, the numbers drop dramatically. In fact, they disappear altogether when you get down to, well, you see they've gone completely here. And they're pretty well gone here too. These ones are probably, they're all on the edge, so they probably shouldn't really be counted, but never mind. They're certainly gone by when you get to the 2 to 1. If you're honest ellipses that really look like ellipses, there aren't any, or virtually none. Okay, now I have to find my next picture. Yes, sorry, I have to, I'm not familiar with the procedures here. Can I just find the next one?
Those?
Perhaps if you hang around here might be good.
Sure.
Yes.
Is that one?
Yes, let's have that one. Yes, this is just nice seeing it on a, this is again the 3 circle, the real sky, looking at these 3 circles. That's the South Pole where you see more going on than in the North Pole. And you see, let's have a look at the next one. That's the North Pole. It's a different projection, sorry. Anyway, let's go on.
South Pole?
Yeah, that's the South Pole. It's good, just go on, I think.
Well,
that's all the WMAP. That is the data produced by the, oh, no, I want the first one that we were looking at. Can we do that? I'm not sure. The order of them must have got mixed. Oh, that's it. Yes, that's it. Good, fine. Okay, I can do this now. That's a simulation. You'll notice they look extremely different. Not just that there are far fewer of them. The colors are not extreme. They're randomly looking. They're all sort of greenish all the way over. You don't see any particular big ones. Notice that we find quite a few, quite large ones, like these ones here, quite big ones. You don't see any of those in the simulation. But that's not what we're depending on. Now this is the more recent Planck satellite. The others were the old WMAP one, which has been going on for a decade or so, I'm not sure how long. The Planck data was only released less than a year ago, and the same analysis has been done here. This is now looking for, it looks like at least 4. Now this must, I think that's only 3, I don't quite know, it says 4. This is looking for centers with at least 3. You notice that it's, rather than disappearing with this more precise data, it's more defined, better defined. I can't quite remember what the number is there, never mind. Yeah, this is the 3 or more centers. This is the 4 or more centers, that's right. And you still see these very concentrated regions like here and so on. And they're very similar to what we had before, but in a way more pronounced. Except that I'm saying it wrong, am I? A little confused. Yes, this is the 3 or more in the Planck data. That's 3 or more circles in the Planck data. This is 4 or more in the WMAP data. This is 4 or more in the Planck data. And you see these huge concentrations in certain regions. This would be a very distant source, and the other ones got smaller for some reason. I mean, obviously these things will have to be looked at by other people more carefully. The Polish group, oh no, this is still our lot. This is just showing you the centers. And what's very striking is that although the criterion for looking for them was simply nothing to do with the average temperature, it was just choosing them because you're looking for the low variance circles, where the variation in the temperature is particularly low. And what you find is that is extremely correlated with the temperature. So you have some regions where they're very warm, other regions where they're cool. The explanation would be, on my scheme, that this is a very distant source in the previous eon. That is a relatively close source in the previous eon. And that is why you see the temperature clumping in this way. It'd be nice to see an explanation from the point of view of inflation or something. I can't see how you would get things like this. Okay, now I've got to go on to the next one. It's to the... Can I move it to the left, or... yes, I want the Polish one. That's the next picture. What? I should be doing something here, shouldn't I? Perhaps you better do it.
Yeah, is it in there?
Before yes, it's the next one in this. Yeah.
That one?
It's that one, yeah. That's right. Okay, this is Planck data again. And this is the Polish group. Now you see, they use a completely different criterion. They don't look for concentric sets. They look for things with a sharp edge, either on the outside or the inside. And you notice that they're very clumped also. Now, I can't think of any other explanation than something along the lines. You see, if you see some red ones, you see lots of them. This means the temperature goes up sharply. Now, if it goes up sharply, it doesn't mean that the average temperature is big or not. So why should you find lots of red ones all in the same region, where suddenly it goes up and then it tails off, up and tails off? And the blue ones also seem to be crowded. Now, that's where it goes down and tails off, downs and tails off. So you get that clumping of these regions, and that would be explained on the kind of scheme that I've been describing. I don't know of any way of explaining it in any other way. It would be interesting to see, and these have been very well done, the pictures here and the analysis. As far as I can see, there's nothing to complain about. Of course, other people should look at it very carefully. But what's going on? Well, I can give you an explanation of what's going on, but maybe that's not the right one, and maybe it's something else. But it would be very interesting to see what, and I think I'll stop at that point. Thank you very much.
Thank you, Professor Penrose. We have some time for a Q&A session. Does anyone have any questions? Yes.
So I always thought of a conformal transformation just as a mathematical tool for bringing infinity to a finite distance. So,
well, that was the original idea. It was just a mathematical tool. I mean, it was an idea that I put forward in the 70s, I think it was, 80s. Can't quite remember now. Just to try and get nice ways of looking at the energy carried by gravitational waves. So you wanted to rather than doing complicated limits, which is what people tended to do, you just have this geometrical way. You squash infinity down, and you could see that that's, for infinity, it's quite a general technique. And then you can see the values that are at infinity. It gives you the radiation field for electromagnetic field or for gravitational field, and then the formulae for energy carried is something you can do on a fairly local basis out at infinity. It's much easier than taking limits. So that was just, as you say, a mathematical device. Now here, of course, we were doing it without worrying about the cosmological terms. So you're looking at asymptotically flat spaces. And there you have an infinity which is null. And it has its own problems. It's easier in some ways and harder in others. But with the cosmological constant, it's space-like. And that you can quite easily see from the mathematics. And if it's space-like, then you can contemplate this scheme of mine. Because the singularities are likely to be space-like too. If you didn't have the cosmological constant, this scheme wouldn't work.
I guess kind of what I was asking is that, well, I mean, so are you saying there's actually a physical process which is, because what I'm trying to hard to visualize how you attach a small point, which is how I visualize the Big Bang, and
I think one of the troubles is that people tend to think of the Big Bang as a point.
right.
And you always see these, well, you know, when the universe was the size of a grapefruit, and then when it was the size of a pea, and so on. But that's misleading. When you think about the causal structure, which in fact is what you're always looking at, so you're looking at light rays, it's much better to think of it as a surface.
Okay.
And in fact, it's related to the problem people always had, is how are these, you see, if it was a point, you see the light cones are kind of pointing right out like that. How can there be a causal influence between them? Because as soon as they've left that point, they're completely out of causal contact. Now you can see that in the space-like picture because their light cones are like that.
Right, yeah.
And they become in causal contact later, but they're simply space-like separated. They're nothing to do with each other.
Yeah.
Which is a problem if you think of the Big Bang as a point event.
Yeah.
But you see, causally, it's a surface.
Okay.
And we've got used to that idea just from the mathematical tricks, you see. It's a matter of getting used to it, I think.
Okay.
But once you got used to it, and it's much closer to the physics, because the physics is pretty well light-like things. It's photons or things of very high energy that you're talking about there. And the causal nature is crucial. So you can understand it's really a lot of separated points. What is it that connected them? Well, it was the previous eon.
Yeah.
If you've got a previous eon sitting there, then it all becomes nice and causal, and you're looking at pretty well classical differential equations. One of the beauties of this, except that I might lose a lot of friends one way or the other, you see. My cosmologist friends who are wedded to inflation hate me, and my quantum gravity friends who are wedded to the Big Bang is the place where quantum gravity makes its mark, you see. And I'm saying, no, you can treat all these things with classical equations. Quantum gravity hasn't got much to do with it, which is a great shame. I used to say the same thing. This is the great laboratory for testing quantum gravity. But on this scheme, no. You just need to have a way of handling infinity and putting it into the equation so that the equations work and become finite equations. And that requires a bit of reorganizing, phrasing things in ways where you just get ordinary differential equations. And it makes mathematical sense. I mean, there are some questions which still need sorting out, but at least the framework looks as though it makes sense.
I have two questions with apologies if I'm asking about something which you've already addressed in the course of this talk. The first question is, when people looked for these concentric circles, was the search biased by the fact that they actually looked specifically for circle shapes, or did these shapes just turn out to be circles? And
Well, yes, go ahead. Yes, sorry.
And the second question is, how do you get in your scheme from one eon with no matter in the end to the next one with matter and mass?
Well, it has to be, I mean, something like a Higgs mechanism. You see, I actually didn't make this point here, but when you get close to the Big Bang, you go back in time, then you get to a time very early on where the temperature was higher than Higgs mass temperature. And before that, you effectively have just massless physics. So that's conventional. That's nothing outrageous there. When you go closer to the Big Bang, the dominating physics becomes more and more massless physics. And so conformal geometry is the right geometry for the physics. Okay, there might be things, anomalies and all sorts of things you've got to worry about. To what extent is this completely true? But the general feeling is certainly that's not where the thing is unconventional. The general feeling is that you have massless physics going on in the very early stages. Now, what's not so conventional is why you have massless physics in the remote future. But that's why I'm saying that I need a sort of inverse Higgs, where the mass, when the temperature gets very, very, very cold, you need a reverse process. Something like that. Now, I mean, these things need to be worked out. I'm not saying that it's all sorted out. You had a beginning question, which I'm not sure I addressed.
I asked about these concentric circles.
Oh, the concentric, yes. Well, of course, we did look for circles and not squares originally. But we looked for ellipses. And that's, okay, we didn't bother to look for squares. I did suggest my colleague, why don't you look for squares? And he wouldn't do it. Too much trouble. But the looking for ellipses is relatively easy, because you just twist the sky. That's an easy transformation. Use the same algorithm, exactly the same one. You looked at the old sky. That's the same. The sky is twisted, but it's the same as twisting your circles. So you're looking for elliptical shapes in the real sky. And you see the numbers drop dramatically. So, okay, we were still looking for circles originally, of course, because that was what the theory said. But we now, after that, look for elliptical shapes. And the poles, I should say, also completely independently have looked at their data, and they find a dramatic drop-off when they look for ellipses. So certainly it's circles over ellipses. There's no reason to believe that squares are there. Of course, if somebody wants to look for them, I'm quite happy for that. Equilateral triangles and things like that. But it's just a nuisance. But ellipses are easy to look for. They're not even quite ellipses. They're slightly distorted, almost ellipses.
As you're going up your timeline, up the page, and you've got these various cylinders joined on,
yes,
one on top of the other. I'm just interested, sort of, how do you get from one to the other? Do you sort of get like an infinite time and you actually never get there, or how do you actually get over the line? So when the universe realises that we've got eon,
yes, yes,
become the next one.
Well, I mean, how you do it is with mathematics, but that's not what you want to know, is it? I mean, you have to have a mathematics which carries you across sensibly. But the idea is, well, the whole question is, who's measuring time out there, you see? Well, especially if mass fades away. If mass fades out, then the clocks I was talking about actually are not very good for the very remote future, particularly because it's likely that if the mass fades out, it will do so in different rates for different kinds of particles. Now, if all of the particles uniformly went out, then you might have a big question about which metric do you choose. But I choose the metric for which the Einstein equations remain true. Now, if you use a metric in which the mass fades out, and you use that metric, that is to say, the clocks defined by the particles, then you will find a violation of the Einstein equations, because it will look as though the universe is contracting with no source to it, in a sense. But if you let basically what I say, you let the cosmological constant determine the metric. Because the cosmological constant is another place where the scale is broken. That's not much good for building a clock in practice. But on the cosmological scale, it does determine a scale. And I say that is, in fact, I try to suggest, this is a crazy idea, but I try to suggest that you could use units. See, people are used to using Planck units. The Planck units are, say, take Planck's constant to be 1, the speed of light to be 1, or Planck's constant over 2 pi to be 1, speed of light to be 1, the gravitational constant to be 1, Boltzmann's constant to be 1. And then you've got all your units fixed. They're a bit absurd, but they're fixed. Now, I'm saying something a little bit more absurd. I don't make the gravitational constant equal to 1. I say make the cosmological constant equal to 3. The reason for 3 is a technical point. But if you make it 3, the equations are much neater when you're talking about what happens at infinity. And it's just a choice of units. But that is sort of saying that the cosmological constant is fixed, and it determines ultimately the scale of the metric. So there is a fixed scale which tells you how to keep things under control as you go from one eon to the next. But I'm afraid it does depend on the mathematics. And there are also some questions in the mathematics which are some slightly different things you might do. It's not completely obvious which is the best. Some of my colleagues have different ways of doing it. But they are perfectly well-defined equations. And you have to say, well, the physics follows that. Although it's infinity, there's nobody around to think of it as infinity because it's only massless things. And as far as they're concerned, infinity is like anywhere else. It's an idea you get used to, like the earlier question, you see. One gets used to playing around with squashing infinity around. When you're talking about massless fields, gravity and electromagnetism, you can look at infinity and see what they're doing out there. And since they don't have any mass, they're quite happy out there. The equations are quite happy when you describe them out there. But it's a slightly difficult idea because we're used to thinking in very metric terms in our physics normally. But when you don't have mass around, it's not such a natural thing to do. And the conformal geometry becomes a more relevant type of geometry.
But what about the other side when you get to, when you get to the next one? When everything's got to start up again?
Yeah. Well, you see the way, yeah, okay.
How does everything start up at once? Why doesn't some parts of it get left behind on the old eon?
Well, the idea, I mean, you need to have I have a thing which I call the reciprocal hypothesis. The idea is that the conformal factor you use post-Big Bang is the inverse of the one pre-Big Bang. So it's as though changing the scale factor to its inverse, 0 goes to infinity, infinity to 0, the way I think about it is the following. You can use the old metric, if you like. The universe gets thinner and thinner and thinner and thinner right out to infinity. You cross infinity, and then you have on the other side a collapsing universe coming from the infinite to infinity coming in. What you find from the equations is that the collapsing version of your universe has a negative gravitational constant. And the idea is that that becomes awkward for the universe. It doesn't like that version. It prefers the other version. It prefers the gravitational constant to be positive, and you have a different interpretation, which uses the inverse conformal factor. And then that creates a whole lot of scalar matter, which is the initial dark matter I'm claiming, which is necessarily there, and is the dominant form of matter in the initial state. It has to decay away in some way or another, or else it would build up and be there at the next eon. You don't want that. There is some, I believe, indirect evidence that it does decay, but I wouldn't take that too seriously. But the point is that you need to make some interpretations, and I do. I say that, well, first of all, that there is a decay of rest mass to make sure it conformally works at the crossover, and that there is this new, that the inverse conformal factor is the one to use in the next eon. It's the more physical one because your gravitational constant has become positive again, and there is then a Big Bang, and you have the dominant matter is this scalar material. And then matter, the rest mass, other kinds of matter acquire rest mass through some Higgs-type mechanism, and you're with the next eon, is the idea. Of course, there are some guesses and speculations involved in that, I fully admit. But it does seem to present an overall picture which seems to be consistent. Not too much freedom in how you write your equations, still a certain amount. Not too much freedom. And seems to be consistent with observations like this. If it's some other theory you want, you've got to explain these things. You've got to explain why the effects are very clumpy, which don't seem to be consistent with the inflation picture. Maybe there's another way of getting that out. I'm sure people will think of some way. Why is the entropy so low? Well, you see, in this scheme, just simply the way the conformal factors work, gravitation is killed off dead. The information is not. It goes into this initial dark matter. So it goes from the gravitational degrees of freedom and the gravitational waves into this initial dark material. And so that picks up the information that was there in the gravitational field, but it's not there as gravitational field. And this gives you the very special initial state that we seem to see. I'm not saying it has to be like that, but I'm saying that at least it does give you a way of looking at many of the puzzles which are not even addressed in most cosmological schemes. Such as why the entropy was so low in this very particular way. It gives you that.
Okay, I think that's all we have time for today. We do have refreshments at the back, so please do stick around.